So I'm from National Renewable Energy Lab, which is a Department of Energy funded national lab, and we are one of the 17 national labs in USA. Um, my name is Adarsh, and people call me Adarsh. That's okay for me. I kind of wear multiple hats within NREL. I'm a group manager. I manage a group on planning, operations, as well as I also lead business development, which is we as a national lab, we also work with non-Department of Energy partners. Could be Duke Energy is one of the example that we are working with, understanding some of the implications of future grid. So let's go to the next slide. Let's click 3 times. One more, one more, one more. Thank you. So NREL has so many wings of research. We have quite a bit of cybersecurity research, quite a bit of materials research, whereas I myself am representing power systems engineering research, which is we at our center look at all the research and development that goes from materials such as power electronics that enable a grid integration to all the analysis that goes to bulk power system, everything in between. That's what this slide is trying to represent, which is we look at physical layer, institutional support layer, and everything in between. Moving on to the next slide. This slide is a futuristic look at things. One of the main topics, energy storage, right? So as and when there is more renewable integration happening, there is more intermittency. There is no way anybody can predict the future, how cloud moves or how storms go or anything of any sort. Whatever we do, there is a limitation there. One way to deal with all the uncertainty when it comes to renewable integration is moving electrons to molecules and moving molecules back to electrons. That's what this slide is showing. If I have so much renewable integration happening, I can use them instead of storing them as electrons, I can convert them to hydrogen generation or something else, or so many things that we can do, then bring it back to electrons when we want. That's one thing that we are eagerly looking at, and there's a very big facility that we are building in Boulder to analyze this one question. The next slide. Moving on to the crux of the slide deck. What am I going to talk about is energy storage, as Rick pointed out. So technologies that are entering the grid, such as solar, controllable loads, could be demand response, electric vehicles, all of these are affecting the regular paradigm of grid. That's what we all know. That's why we all are here. And the new challenges that are coming in, the only way to work around with is to embrace them and convert these to opportunities. And that's what the energy storage is all about. As and when there is more renewable integration happening, if you have a lot of storage, then that's great, right? However, before I go and say storage is great, I'm going to get into some of the economics of why storage is becoming so popular and what are the limiting factors in the near future. The next one more click and one more. That's good. The question here is, why do we need storage? If somebody has some questions about that, this is a very, very fundamental basic slide, which is one of the main need for storage is to balance the load. Not every time, every second, we can balance load and generation. That's where the whole markets and RTOs and everybody exist. Whereas with storage, we can actually leverage these intermittent changes and shift or balance the load with charging the storage when we want and discharging when we want. That's the freedom that we get. However, going to the next slide, why is storage becoming a big deal? I'm doing research in electrical industry from the past at least 10, 12 years. In 2009, storage was not as big as today. That's what everybody agrees here, I think. In fact, in 2008, I wrote my first electrical IEEE paper, and that was a very rare paper to see. Now there are like 100 papers every day, I guess, on storage. So this is what the main thing that's making storage so popular is because the costs are dropping down. That's what you can see on your left side. And on the other side, there is a significant improvement in renewable integration happening. So one is driving the other. In a way, more renewable integration needs storage, and more storage, the costs are reducing, is enabling more renewable integration. It's like a It's like a chain that's happening here. The next slide. Um, can anybody buy storage? Yes, you can buy a big storage today, tomorrow, whoever, whatever size you want. If you want lithium ion, you can go ahead, you can buy whatever you want. But however, the realities are this. That's what this slide is trying to say. Storage should be cost effective. And nobody will go and buy a storage that's crazy expensive just because it's out there and it's going to save me from a storm, unless it's cost effective and we find a reason to use it. Second thing is, the market should evolve and be able to monetize the services. If I buy a big storage and if I use it for my own good as a backup, it's not monetizable necessarily, although I get a satisfaction of electricity. Services that I use the storage for should be monetizable. If I do not monetize them, I cannot get value out of it. The next thing is technical requirements. Not every storage can do everything. Some storage is good for seasonal storage, whereas some storage is good for frequency support. Technical requirements and integration. Now, if I look at 2 and 3 together, combine and then becomes question as to how can I make my grid more renewable rich. So all of these should work together. That's what makes renewable interesting. Next slide. This is just a customary slide that I put. A storage can provide regulation services, can provide load following, which is diurnal support. Storage can also provide energy shifting over seasons. And storage can go from supercapacitors, ultracapacitors, all the way to seasonal thermal or hydrogen, all the way. It's huge. Market is very big, to be honest. Next slide. As of today, if I go to California or Midwest ISO or any other regulatory operated systems, today I can go and bid my storage in so many things. That's what the table here that you can see. Storage can provide local grid support, could provide arbitrage, could provide frequency support, could provide transmission deferral, black start, numerous things, right? So now what I'm going to do is I'm going to take all this content, break them into 4 rows in a table. That's what I think the next slide should be. I can move the next slide. Right. So now I'm going to look into 3 classes of service. A storage can provide capacity, energy, or ancillary services. That's what 99% of the storage services fall under. Capacity is kilowatt, the power demand. When there is a peak load, I can use my storage to provide capacity, whereas when needed, I can use my storage to provide energy. That's my second service. And the third is ancillary services, which is mostly fast services, rapid responses, and quick frequency changes, such ancillary services. Next slide. So I'm going to fill this table up. So in order for me to buy a storage today, and if I want to buy storage and I want to put it in California ISO or Midwest ISO today, let's look at what are the economical factors that what are the target prices that one should achieve to make energy storage feasible in a reality. Unless somebody wants to go and buy, that's a different decision altogether. So let's go to the next slide. Essential reliability services is what I'm referring to as regulations. A storage can provide frequency support as and when needed, because load and generation doesn't go back to back all the time. You need frequency support, and that's what the storage can provide. Next slide. This market is not so big in the sense this market is only good for a few gigawatts, a few tens of gigawatts, and the duration for this is not exceeding 1 hour. And for this to happen, the cost of system should generally the market can provide up to $1,000 per kilowatt. That's what a storage can provide. If I buy a nice storage system, this is what target I should be looking at. Next slide. The next is capacity. Pumped hydro or a very big peaking plant can be used for capacity. Next slide. Capacity, if you can look at it, can compare to operating reserves, capacity market is very big. I can go up to hundreds of gigawatts for capacity, whereas I cannot get $1,000 per kilowatt, whereas I can only get up to $300 per kilowatt hour. So here there's a shift in unit and complication there. So if a utility wants to go and buy storage today, they can, but there's so many layers that people should look into. That's where the challenge is coming from. And the market duration goes from 4 to 8 hours. I can charge my battery during when there is sun or when the excessive wind. I can discharge when there is peak in the evening. That's what the capacity is. Next, this is diurnal. This is a very big market. So the question here is all about willingness to store and not store. Um, Diurnal shifting happens when there is solar generation happening. But the question here is in California or other markets, when there is excessive renewable generation happening, they give negative pricing. That means they pay you to charge your battery. With that said, the costs of payback for a battery further reduces here to $100 per kilowatt hour. So as I keep going to longer duration storage, the costs keep dropping down. And the question that I'm walking out of this time that I have is if I go for a seasonal storage, in the sense, if I want a very big grid, if I want a seasonal storage, and there is, I want to store it in winter and use it in summer or vice versa, what is the cost I should be looking at? So long duration storage or any sort of storage that the world is heading towards is a very big question on the table. And we at Enrel are taking this very seriously. One example is working with Duke Energy to understand the implications of a utility like as big as Duke walking towards more and more renewable, and how are those gonna bring new questions to utility as to what sort of storage should they buy, what sort of controllers, what sort of investment should they make, and that's what we are looking at in general. I think that should be us. Yeah. Thank you all for the time, and we can get the questions later. Thank you.